I'm Ping-Lun, and today I'm going to talk about how to build practical microarchitectural word machines. So this talk is not about the new microarchitectural side channel that can steal secrets. Instead, I'm going to show you how to build a computer inside the microarchitectural world. If some of you are expecting a new side channel, then I'm sorry to disappoint you a little bit, but I think our work is even more surprising, and I'll explain why. When we look at the processor from a software perspective, we normally treat it as a black box and use the ISA as an interface to the hardware. If we open this black box, we find many microarchitectural components, and this work studies the code gadgets that can perform computation using microarchitectural side channels, and we call them as a word machine, a microarchitectural word machine. And there has been a lot of recent work on designing and building these microarchitectural word machines. For example, there's an important paper in this field called The Gates of Time, which appeared here at USENIX last year, and is actually from UVO. This is a very good paper, and it showcases how to use microarchitectural word machines to perform cache attacks and amplify cache signals. But beyond that, these microarchitectural word machines have the potential to support many more applications thanks to their special characteristics that make them very difficult to analyze. For example, they can hide the computational states inside the microarchitectural world. So now the computational states will not be visible architecturally. And also, they can prevent both static and dynamic analysis because they run low-level logic gates using microarchitectural components. So this seems like these microarchitectural word machines are a great candidate for program obfuscation, and people should have been using them already. However, this is not the case because existing microarchitectural word machines are not scalable and very difficult to program. This diagram shows that existing work suffers from low accuracy when running large circuits. This means that they cannot correctly compute complex computations like the AES encryption. And this code snippet is Paraworks' implementation for the SHA-1 hash function. It contains a lot of low-level details, so only experts are able to create a new word machine. This motivates us to propose Flexo, a new design for microarchitectural word machines. Our new circuit construction significantly improved the scalability, and our compiler makes it much easier to create new word machines. With these improvements, we are now able to obfuscate real-world programs such as the UPX packer. In the rest of this talk, I will first give a brief overview on word computation and then move on to our Flexo word machines. So now, let's compare the differences between normal and word computations. Word computation takes place inside the microarchitectural world. So instead of using the ISA instructions for computation, we now need to use word gates to compute with the microarchitectural states. These word gates are built from the memory operations that happen during transaction execution, and transaction execution occurs when instructions are executed but never committed, and they are ultimately squashed by the processor. This means that every architectural changes created from these word gates will be reverted by the processor after the transaction execution, so we are not able to use these word gates to modify the values inside the registers or the main memory. So now, we need to store the values inside word registers. And these word registers are built from the cache recency information, and their value is 1 when they are in the cache, and their value is 0 when they are out of the cache. Here is a concrete example of a word gate. We use an if statement to trigger transaction execution, and inside the if condition, we will mistrain the branch predictor to force the processor to mispredict into the if statement, where we will transiently execute a where AND gate. This where gate takes 2 where registers as input, and it will output to another where register. This where gate computes the AND operation by using the SS latency to the input where register to control the output. And here is a diagram that showcases when input where registers have different values, then they have different SS latencies. When both inputs are 1, then both of them are in the cache, and they have very short cache hit latency. But when they are 0, then both of them are out of the cache, so they have a much longer cache miss latency. And this AND gate will try to fetch the output where register into cache when after it fetches both input registers. So it is only able to fetch the output when both inputs have very short cache latency. When any of the input is 0, then the much longer cache miss latency prevents this gate from fetching the output, so they end up output 0 after the transaction execution. Firework has used similar techniques to build other logic gates like the OR gate and the NOT gate. But our work does not follow this design as we propose a new circuit construction for our FlexOware machines. Our new circuit construction adopts the differential encoding for binary values that we will use two wires to represent a bit. We call these two wires as the plus wire and the minus wires. And to represent the binary value 1, we set the plus wire to 1 and the minus wire to 0. For the binary value 0, we do the opposite and set the plus and minus wires to 0 and 1. When these two wires have other values, then we treat them as the invalid states and we will later use them for error detection. At first glance, this encoding doesn't seem to be very useful, but it actually provides us a lot of benefits. The first benefit is that we can now build much more scalable gates. Similar to the lookup tables in the FPGA circuits, we can now construct a weird gate directly from its truth table. Even though I don't really have time to cover the technical details about this conversion between a truth table and a weird gate, under the hood, we are using OR and AND gates to compose the truth table inside the weird gate. And this conversion works well for any logic gates with no more than 4 inputs. This means that we can now build much more complex gate like the XOR gate or even a huge 2-bit adder using only one single weird gate. In contrast, Firework can only build basic logic gates like AND, OR, and NOT gates. And our new encoding allows us to perform error correction with dynamic voting. Firework is also doing error correction, but they're using the 3 out of 5 majority voting, which will rerun the circuit for 5 times and output the majority results. This error correction scheme has a deficit, like it will cause a fixed 5x overhead to the circuit, and it may not be able to fix most errors when circuits have low accuracy. On the other hand, our work adopts the dynamic voting mechanism to perform error correction that we will only rerun the circuit when it detects an error. So now, we have a dynamic overhead that is much smaller than Firework's overhead, and we can fix most errors even when the circuit has extremely low accuracy. Like for a circuit that has 0.3% of accuracy, after the error correction, we can fix it to 99.9%. Another contribution of our paper is the first compiler for microarchitectural word machines. In the beginning of this talk, I showed this code snippet to talk about how difficult it was to create a new word machine. But now, with the help of our compiler, programmers only need to write this high-level program to achieve the same computation. They don't need to worry about the low-level details because they are all handled by our compiler, and our compiler will perform optimizations to the circuits so that it can have much higher accuracy and performance. So with these improvements, we can now move on to see how they contribute to our experiment results. We run our experiments on 8 shared AWS EC2 instances with different microarchitectures as shown in these tables. We generate our FlexOware machines using our compiler and compare our results with the Gates of Time paper on the Skylake machine. We only compare with them on this machine because they don't support other microarchitectures. So now, let's compare with the Gates of Time using 2 small circuits, a 4-bit ALU and the first run of the SHA-1 hash function. For the circuit size, by using our new circuit construction, we can make our circuits 4 to 8 times smaller than Firework. And for the accuracy, the stripes on top of these bars indicate the increasing accuracy when we turn on error correction. And this diagram shows that Flexo has a much higher accuracy than the Firework even without error correction. For the runtime, we must set the y-axis to low scale, otherwise the runtime of our ALU will not be visible in this diagram. So it is obvious that Flexo is much faster than Firework, and the overhead of our error correction scheme is also much smaller. Even though here we're using 2 small circuits for comparison, Flexo can actually support much larger circuits, like the whole SHA-1 hash function and the AES encryption. For these 2 crypto applications, both of them can achieve very close to 100% of accuracy on all these machines. And for the runtime, our SHA-1 circuit takes around 15 milliseconds to compute, and this is 20 times faster than the state-of-the-art. For AES, it takes around 200 to 350 milliseconds, and even though this is much slower than a normal AES using like ISA instructions, but this is the first AES microarchitectural word machines in the literature, and this is fast enough for many applications. In fact, we use AES encryption in our proof of concept application, the UPX packer obfuscated by Flexo. The UPX Packer is a popular tool widely used by malware because it can prevent static analysis by compressing the code and data inside a program. We obfuscate this UPX Packer by encrypting the pack binary using AES or semi-encryption. And at runtime, we will use a flexible word machine to decrypt the pack binary. And this makes reverse engineering much more challenging. For the unpacking speed, it takes around 1 minute to unpack a binary that is 132 kilobytes in size using the semi-decryption, and AES takes around 5 minutes. Although this is much slower than a normal packer, a slower execution speed does not really matter for attack scenarios like a malware attack. Also, the obfuscation provided by Flexo can defeat many existing antivirus tools. So in conclusion, Flexo makes microarchitectural word machines much faster and more accurate, and our compiler makes it much easier to create new word machines. So now, microarchitectural word machines are a practical threat, and we should expect to see them in program obfuscation techniques or other types of attacks in the near future. Thank you for listening, and I'm happy to answer any question.